Last video we learned to condition, to update the probability of an event once we know another has occurred. Now we use conditioning for a different job, computing the plain, unconditional probability of an event that is hard to attack head-on. The trick is divide and conquer. Break the sample space into a handful of scenarios, work out the probability inside each one where it's easy, then stitch the pieces back together. That recipe is the total probability theorem, and it is the bridge to Bayes' rule in the next video. First, we need the right way to carve up the sample space, a partition. Recall the idea of a partition. A collection of events A1, A2, up to AN is a partition of the sample space when two things hold. The events are disjoint, no two overlap, and together they cover everything. Their union is all of omega. Picture omega as a rectangle sliced cleanly into colored tiles. Every outcome lands in exactly one tile, no gaps, no double counting. That exactly one is the whole point. It is what will let us add probabilities without any fear of overlap. Now drop an event B onto this partition. Wherever B falls, the tiles cut it into pieces, the part of B inside A1, the part inside A2, and so on. Since the tiles are disjoint, these pieces are disjoint too, and together they reassemble all of B. By the third axiom, the probability of B is just the sum of the probabilities of those pieces, the probability of B in A1 plus B in A2 and so on across the partition. Here is the key move. Each piece, by the product rule, is the probability of its tile times the conditional probability of B given that tile. Substitute, and out comes the total probability theorem. The probability of B equals the sum over K of the probability of AK times the probability of B given AK. Read it as a weighted average, the chance of B in each scenario weighted by how likely that scenario is. Let's put it to work. Two urns sit on a table. The first holds 5 green balls and 3 red balls, the second 3 green and 9 red balls. We flip a fair coin to pick an urn, each with probability 1/2, then draw a single ball. What is the probability it's green? Condition on the urn. If we picked urn 1, green has probability 5/8. If we picked urn 2, green has probability 3/12, 1/4. Total probability stitches them together. 1/2 times 5/8 plus 1/2 times 3/12, which comes to 7/16. Notice we never had to reason about both urns at once. We solved each easy case and let the theorem average them. That is the power of conditioning as a computational tool. Divide the world into cases, conquer each, and average. Next, we run this machinery in reverse. Given the ball came out green, which urn did it most likely come from? That inversion is Bayes' rule.